So last time, moment of inertia. And what we're really talking about here is the mass moment of inertia about a point. So I would recommend, like, when you take future classes where they talk about the mass moment of inertia about a point and they call it the moment of inertia, you should, sort of like angrily interject that they should clarify whether they're talking about the mass moment or the area moment. And the same thing with, like, in deform or whatever, when they talk about the area moment of inertia, you should probably bring that up. Professors like to be corrected in a snippy way. So I talked about the integral definition. And that is the moment of inertia about A is equal to the integral over the entire mass of r squared dm, where r is the distance from the about point to each individual bit of mass. And so the basic idea, yes? Okay, so if this is the body, and you've chosen this as the about point A, then for each little infinitesimal piece of mass, this has a mass of dm, and it's a distance of r from that about point. And if you add up for each one of these infinitesimal pieces, if you add up r squared times the mass of that piece, for every piece, you get the mass moment of inertia. Yeah, it's just like, it's an infinitesimal piece of an entire mass, and that infinitesimal piece has some location in space, and so it has some distance r associated with it, and you're calculating r squared times dm for that piece, and then you're doing it for the infinitely many other pieces, and then you're adding all those up, and that gives you the moment of inertia. Nope, just masses. Just masses and shape. And the way what this ends up doing is giving you high values when a lot of mass is spread far from the about point, and gives you a low moment of inertia when things are packed tightly close to the about point. We're not going to use the integral formula. We're going to use just simple formulas that come from this definition. Before I go into those formulas, let me give you the units. So from this integral definition, what are the SI units going to be? Kilogram meter squared. Close, yep. Of inertia about a point. So kilogram meter squared. And it's whatever units you're in, it's going to be in units of mass times distance squared. So now I'm going to give you the moment of inertia about A for 4 simple shapes. And this is all you're going to need, these formulas, for doing the moments of inertia in this class. That's right. You're exactly right. Although in this class, I'm not sure that that's going to come up at all. Maybe towards the end. But yep, you're exactly right. The first one is a slender rod. So there's the rod, and let's think of a coordinate system with its origin at the center. The x-axis pointing along the rod, y-axis up, and z-axis that way. The moments of inertia, first about the x-axis. So now we're thinking about this shape's resistance to rotation. If this was like a pin that it was rotating around, it is spinning the cylinder. You know, since we're assuming that this is slender, we're assuming that the radius or diameter of this is 0. So none of these points are assumed to be any distance from that axis. And so the moment of inertia about that x-axis is 0. The other two are going to be something, though. And so to flip this rod, if you're talking about a rotation where this rod flips end over end, and if you think about it doing that around the z-axis or around the y-axis, it's really the same shape. But the moment of inertia about y is equal to the moment of inertia about z, which is 1/12 times the mass times the length squared. This whole length here is L. Yeah. Yes. Yeah, you can program them in. Okay, so with all of these, what's being set up here is a thing where you're going to have to imagine with these shapes which way this thing is rotating. Are we talking about, in this case, I mean, there's really never going to be cases where we're calculating how a slender rod would rotate about its, you know, like just a cylinder, because it doesn't have any resistance to that rotation. That wouldn't be a way to calculate that. But with all of these shapes, there's going to be different properties if it's rotating about one axis than if it's rotating about another axis. And so you're always going to have to keep that in mind. And notice also that these are all for about points at the origin. So we're talking about that being the about point A. Another question, Ryan? Oh. If it's bending? Yeah, this is all rigid body stuff. Yeah. So if you're talking about something that's having significant deformation as the dynamics are going on, you're talking about putting dynamics, like I mentioned before, you know, and then things get more complicated. So this is all of these calculations are things where it's a reasonable approximation to say that it's rigid. The next thing is a thin rectangular plate. And we'll call this distance B, and this distance C. The thickness, just like we assumed that slender rod had 0 diameter, we're going to assume that thickness is 0. And our axes are going to be x-axis straight out of the face. The y-axis up out of the thin side. And then the z-axis is that way. And again, our about point is right in the center. So now for this one, you have to think about, there are basically sort of two basic ways that this thing can rotate. It can rotate like a throwing star, you know, like a blade, like throwing an axe, you know what I mean? Where the sharp thing is cutting through the air, or it can rotate like a paddle. What axis would it be rotating about if it's rotating like a blade? The x-axis, yep. And about the y or the z would be two different paddles. About the y-axis, it would be the long, thin paddle doing this. And about the z-axis, it would be the short, wide paddle doing this.
So assuming like this rotating about x with resistance to rotation?
No, you. The reason that with this there's no resistance to it spinning around like a cylinder is that if you calculate, think of a element of an infinitesimal piece of mass on the outer edge, okay, and we're trying to calculate how far that is from the x-axis, okay. If this diameter is 0, that's 0 distance from the x-axis. And so in this case, all of those r squared dm's add up to 0 and you get no. That's not true in this one. If it's rotating like this about the x-axis, think of an element of mass dm on the outer edge of this. It still has this whole distance r from the x-axis. And so would have no air resistance, I suppose, but that's different than resistance to rotation. So the thin rectangular plate about the x-axis, rotating like a blade, we have 1/12 times the mass times the quantity b squared plus c squared. About the y-axis, we have 1/12 times the mass times c squared. And about the z-axis, we have 1/12 times the mass times b squared. You can think of these as three separate two-dimensional problems, plane problems. And like, for example, if this thing is rotating about the y-axis, okay, imagine this being just a two-dimensional problem where you're looking at it from above the y-axis. What you really have is just a slender rod, because you don't care about the thickness into the page. That doesn't affect the rotation in that plane. And so that's why these two look like the formula for the slender rod. The x-axis is different, though. Okay, so for this one, think blade or paddle. Next one is a thin disc. It's a circular disk, but this is supposed to look like three-dimensional. So the x-axis goes out of the thin side. The z-axis goes straight out of the face of the disk. And the y-axis is perpendicular to those. And again, the about point is right in the middle. So now, again, if you think about this as like rotating as a blade or a paddle, it rotates like a blade about the z-axis. And the shapes rotating about the x-axis or the y-axis are identical. You know, like when you flip a coin, that's like rotating it about the x or the y-axis. Okay. And it doesn't matter which way the coin is oriented when you flip it, the behavior is going to be the same. So we expect different value for the moment of inertia about the z-axis. And about the z-axis, you get 1/2 mr squared. R is what you would expect it to be, the radius of this disk. And then the moment of inertia about x and the moment of inertia about y are both the same. Those are 1/4 mr squared. And so again, with this one, you need to think, is it a blade or a paddle? And then the last one is a sphere. So that's like a three-dimensional circular shape. The about point, again, is going to be right at the center. I'm not even going to draw the axes because it's axis symmetric. And so no matter what your axes, how they're oriented, the moment of inertia about x is equal to the moment of inertia about y, is equal to the moment of inertia about z, and it's equal to 2/5 mr squared. Okay, so notice that all of these, I've only given moments of inertia about the centroid. Well, just a little bit that I've said about using the rotational version of Newton's second law, the moment equation, says that there are two possibilities for your about point using rotational Newton's second law. So we know that there are cases where we're not going to want our about point to be at the centroid, okay? And so if there's not a way to translate from the center of mass, from the centroid, to some other point that we choose, we have a problem, So there has to be a way to use these formulas to represent the moments of inertia about other points, or this has a very limited usefulness, we can calculate the moment of inertia about other points using what's called the parallel axis theorem. So here's the idea of the parallel axis theorem. It's a really useful thing. You'll have to use it anytime your about point is not at the centroid of the object. So it's needed whenever your about point A is not at the centroid. Well, really the center of mass, but those two are the same as long as the thing has the same material through the whole thing. So here's the idea of the parallel axis theorem. Say that you have some arbitrary shape. So this works for any object. And let's say this is the centroid. And let's say this axis is C. And then this axis is A. And this axis is parallel to the first one, but just separated from the axis C by a distance D. They're a distance D apart. And if the axis C goes through the center of mass, and the moment of inertia about A is equal to the moment of inertia about C plus md squared, where m is the mass of the body and d is the distance between those two parallel axes. Okay, that says something about the where you always, in every case, find the smallest possible value for the moment of inertia. Since mass can only be positive, and obviously anything squared, that distance squared can only be positive, this says that any axis that doesn't go through the center of mass has to be bigger than the moment of inertia for an axis going through the center of mass. You can't make the moment of inertia smaller as you move away from the center of mass, as long as you're still rotating about, an axis in the same direction. So one more important fact about moments of inertia. If a complicated shape is built up from n simple shapes then the moment of inertia of the complicated shape is just the sum of the moments of inertia of the simple shapes about that same axis. I'll do an example that shows how that works. So let's say we have this T-shaped object. That's connected to the ground by a pin joint. Let's say the thickness everywhere is 0.1 meters. And this length is 1 meter. And this length is 1 meter. And let's say that the mass of the object is 50 kilograms per meter. So this 1 meter piece has a mass of 50 kilograms. This 1 meter piece has a mass of 50 kilograms. And altogether, it has a mass of 100. And we want to calculate the moment of inertia about the pin. Okay, so we're going to break this up into two pieces. I'll call this rectangle 1 and this rectangle 2. And we're going to, this is going to be A here where the pin is. And so we're going to calculate the moment of inertia about A of 1, the moment of inertia about A of 2, and then we're just going to add those two together to get the total.
The width of A is also 0.1.
Yes. Okay, so we have a rectangle like this. With a length of 1, a thickness of 0.1, and our about point is here. The formula says that the moment of inertia about the center is 1/12 times the mass. The mass of this rectangle is 50 kilograms. Times the quantity length squared plus width squared. And it looks like I calculated that wrong before. Can someone calculate that for me? So here we're calculating it about this point C. That's not going to be our final answer for this rectangle. To 1 kilogram meter squared. But then what we really want is the moment of inertia about A. So we have to use the parallel axis theorem. So the moment of inertia about A is equal to 4.21 plus the mass, 50, times the distance from C to A. What's that distance? 0.5, yep. And that is 12.5, 16.71. No? Any questions? Is that right? Yeah. For the in the parallel axis theorem? Oh, the thickness I mean is this. And so whatever is happening into the page, this could be a mile wide in that direction. We don't care about that. That doesn't change anything. So, you know, in order to have a mass of 50 kilograms, this could be a long plate for all we know. But that doesn't affect how it rotates about this axis. And so the only question is whether it's the difference between a slender rod and a rectangle is, are we assuming that the width this way is 0? You know, no. We're assuming that it has a width of 0.1, but you can see from this formula why, as this gets thinner, that vanishes so quickly because of the square. So if we had assumed, even though this is only a tenth as thick that way as it is long, I mean, that's not really that thin. We still had only a 1% difference between what the approximation would have been as a slender rod and what we got, including that width. Okay, so now member 2, rectangle 2. So there's the rectangle. Here's the center. And RA is down here. So the moment of inertia of this about the center is the same as rectangle 1 was. 1/12 times 50 times the quantity 1 squared plus 0.1 squared. And that's 4.21 again. That's the moment of inertia about the center of that rectangle. But now we have to use the parallel axis theorem to get the moment of inertia about A. The mass of this thing is 50. And what's the distance from C to A? 1.05. Yep, exactly. And so what do you get for that? 56.23? Okay. So notice that even though those two rectangles are identical rectangles, they're equally hard to rotate around their own center. It's much harder to get the second one, like look at the values for the moment of inertia about A. It's much harder to get the horizontal rectangle rotated about A than it is for the vertical rectangle, because this one is so much farther away from that axis. Have you seen, like in Physics 1, did your teacher do the demonstration where you stand on that rotating thing and rotate a little bit with the masses out here and you go really slow and you pull them in and all of a sudden you're going really fast? That's the idea here. The farther the mass is from the axis of rotation, the harder it is to make it rotate. Well, yeah. What engineers tend to call moments, physicists tend to call torques. But yeah, the relationship is that just like F equals ma is Newton's second law, the moment equation says moment equals I alpha. And so the moment is the torque, and the I is the moment of inertia. So you can think of moment of inertia is a resistance to rotation, to the rotation that a moment would produce, the same way that mass is a resistance to the acceleration that a torque that a force would produce. Okay. Okay. Oh, I haven't finished this yet anyways. 59.34. So the total then about A is 16.71 plus 59.34. And what do you get for that? 76.05 kilogram meters squared. Yeah, right. I mean, it could go, like I said, it could go a mile into the, yeah, you're right. It would have to be pretty thick into the board. All right, any questions about moment of inertia? The last thing we have to define is moments. So remember, we're working our way up to this equation that says the net moment about some axis is equal to the moment of inertia about that axis times the angular acceleration. We've defined this one, so we still have to define this, and then we're ready to do kinetics. Well, we have to know what it is. Sometimes we'll know the moments and we'll want to calculate accelerations. Sometimes we'll know accelerations and we'll want to calculate moments. But we have to know what the definition is. So the last needed definition is the moment. And people just call it the moment because it's shorter to say, but it's really the moment of a force about a point. And the idea of this, so yeah, this is what I think in physics was often called a torque. In engineering, a torque is a equal and opposite twisting along the long axis of a bar, and that's why we call this a moment. A torque is sort of a separate thing, but this is what you call the torque in physics. And the idea of a moment is it's the tendency of a force to cause a rotation. And so I like to think of it like this. So that's a bolt. And that's a wrench. And if you're trying to, if you have 200 newtons of force available to turn this bolt, you want to apply that force here, or here, or here. Yeah, that's why, like, if you have a really stubborn bolt, you go get your bigger wrench because you can get farther away from it. If you could apply 1,000,000 newtons of force, to the top of the wrench here, and that bolt will never turn. It'll just rip the bolt in half. But there are two things that matter with how you turn this, with the ability of this force to turn. One is the amount of force, and one is the perpendicular distance from the force to the axis of the rotation. And that perpendicular force, I'm going to call rho, the Greek letter rho. And so the moment, the mathematical definition, the moment of a force about A, before I do this, let me draw. You can squeeze this in over here. So let's say this is the object that you're trying to turn. This force is being applied to. And let's say this is the about point A. And then at this location P, a force is being applied. So let's say this is the force vector F. The rho vector goes from A to P. So there's the rho vector. And mathematically, the moment produced by that force F is equal to the rho vector crossed with the force vector. Where that rho vector is the vector from the about point A to the point P where the force is applied. One thing that means is that if you know the coordinates of P, where the force is applied, and you know the coordinates of A, that rho vector is equal to the coordinates of P minus the coordinates of A. That's one way you can calculate it always. Any questions about that? So this MA net that we need for the rotational moment of inertia is the sum of all moments MA produced by the individual forces. So next time we'll talk about how to use rotational Newton's second law, but remember what that says is add up the moments produced by all the forces about the point A. That's equal to the moment of inertia about A times the angular acceleration, where A is either a fixed point, like a pin joint or a hinge, or the object's center of mass. Okay, so this is going to be a key thing for rigid body dynamics, and on Friday we'll talk about how to use that. Okay, that's all. No, just whenever the syllabus says the next one is. I think it's the next week. We just totally skipped that cycle.